The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
We're going to do the first of 3 lectures on the last topic. We're going to talk about phase diagrams starting today, Monday, and wrap it up on Wednesday. Phase diagrams is related to the question of stability and sustaining the solid state. We've talked about the behavior of solids, and we've used solids in order to teach the rudiments of chemistry, but today I want to talk about the conditions under which solids are stable. And under what conditions do solids remain stable? When do they become unstable? This is important in industry, for example. If you're running a cast shop, you're making auto parts, you want to know what the solidification temperature is of a particular alloy. It's important in failure analysis. Something like the fall of the World Trade Center, looking at the metal specimens to determine what was the mode of failure. The temperature excursions leave a signature, a thermal signature indicative of the history of what happened to that object. And by determining whether something went above a certain phase transformation temperature, we can retrace, reconstruct the incident. And you might say, well, gee, what's the big deal? I mean, you look up in the tables, everybody knows that water boils at 100 degrees centigrade, but maybe it's not so simple. Let's say you decide to realize your life's ambitions and you're going to go climb Mount Everest. So you plop down $10,000, you get a permit from the Nepalese government. The next thing you know, you're at base camp, 20,000 feet. You have a hankering for soft-boiled egg. So you pitch a campfire, put in the eggs, 5 minutes, 10 minutes, 15 minutes. Pardon me, you want hard-boiled eggs. You want hard-boiled eggs. After 15 minutes, you open the eggs, they're still running. So you get really steamed. You go 20 minutes, 25 minutes. Every time. The yolk is still running. The white is converted, but the yolk is still running. What's going on? Well, we talked about denaturing. The white denatures at 65 degrees centigrade. But at 20,000 feet, the atmospheric pressure is reduced to the point that water boils at below the denaturing temperature of the egg yolk. And so you can boil until the end of time, and you'll always have soft-boiled eggs. If you like soft-boiled eggs, you cannot screw up. You cannot screw up. Okay? So what do we know from this little anecdote? This little anecdote is that the boiling point is a function of pressure. So it's not that simple. Let's go to another place. Let's go under the hood of a car. One of my favorite places. Okay, so here's what's going on under the hood of a car. Here you've got the engine, and inside the engine we have combustion, and the combustion gives off a huge amount of heat. We have to dissipate that heat. So we have water channels running through the engine and out to the radiator. And the radiator cools this water before recirculating it thanks to the action of either fan or wind or some kind of movement of air. And so what's the principle here? The principle here is that inside the radiator we've got solid. This is the rad. It's probably made of, in the old days they made them out of copper, but nowadays they're making more and more of them out of aluminum. And we have liquid, which is the coolant. This is the coolant. This is water. And we have a big delta T here, right? This is hot and this is cool, and so we have a heat flux going in this direction. And this is working great because the density of water is high, and so therefore it's able to transfer heat very efficiently. So this is good. This is really good. What can happen if things go out of control? Things go out of control and we start to boil. And you know that the boiling point of water is more or less 100 degrees centigrade. We're down here. We're not at the base camp in Mount Everest. Here's what happens when things start to go out of control. Now we start to get gas bubbles. These are the gas bubbles associated with the boiling of water. And now the heat transfer between gas and solid, is very poor. Think about it. What's transferring the heat? It's the atoms, and the atom density in a gas is sparse. So gas is a very poor heat transfer medium. So we must avoid boiling. If we get boiling, then we get into a thermal runaway situation, because now we got boiling in the first place because the water was too hot, but now we're doing a less efficient job of cooling, and it's going to get worse and worse and worse until finally, boom. So what I want to do is I want to get my liquid range. I want to tailor the properties of the coolant. I want a coolant that will be boil over proof. So if I could raise the boiling point, that would make the car safer to drive under extreme conditions. Typically what happens is you're zooming down the highway on a hot summer's day, and then there's some reason to come to an abrupt stop, and then there's all that heat to be dissipated. And no more do you get the benefit of the motion of the car. Now you're just relying on the fan. So what can we do? If we go to the top of Everest and the pressure goes down and the boiling point falls, could I raise the boiling point by applying more pressure? Yeah, let's put a pressure cap on the radiator. Let's keep the contents of the radiator high, and if you read the top, it'll say 15 psi, which is 1 atmosphere. So I've got 1 atmosphere here plus an extra atmosphere, so I'm running at 2 atmospheres pressure. So that will raise the boiling point and stave off the dangerous gas evolution. And then I can do one more thing. Instead of running pure water, I will add ethylene glycol. I'll add ethylene glycol about 50-50 per volume. You know this is antifreeze. It gives a freezing point depression. We'll talk about that next day. But it also gives boiling point elevation. So in the summertime, you should always run with antifreeze, because the combination of the pressure cap plus the addition of the glycol raises the boiling point from 212, I'm talking about cars, so I'm going to use Fahrenheit here, 212 degrees Fahrenheit to 265 degrees Fahrenheit. This buys you a much higher cushion. So what are we doing? We're tailoring this by making the boiling point a function of pressure, and now I'm showing you that it's also a function of composition. So this whole business of solid state stability, I hope I'm showing you, has a little bit more to it than just looking up the transformation temperature on the periodic table or the handbook. So I want to talk to you for the next 3 lectures about phase diagrams. Phase diagrams are atlases. They're maps. They're maps of stability that answer the question, if you specify pressure, composition, temperature, what are the stable phases? So that's what you need to know. So let's talk about phase diagrams as stability maps. Stability maps. The stability of what? It's the stability of the state of aggregation. It's going to tell us if it's solid, liquid, gas, and under what circumstances. So let's look at some simple phase diagrams, but before we can do it, I need to define some terms for you. So first of all, let's define the term phase. The phase is a region of a substance that has the following characteristics: uniform in chemical composition. It's uniform in chemical composition. The second thing about it is that it's physically distinct. Physically distinct. And I'll give you some rich examples. I want to put this down just to document it, and then after you see a few examples, these words will mean something to you. So it's physically distinct, and in the extreme, it's mechanically separable. It's mechanically separable. Physically distinct and mechanically separable. So let's look at some examples of one-phase and two-phase systems. And this is one of these days where we're using symbols to mean multiple meanings. I've already used P to represent pressure. If I use P now to represent number of phases, you won't be able to tell one from the other, so I feel a little bit Western today, so I'll make it circle P. So circle P equals number of phases, not to be confused with P, which is the pressure. So number of phases I designate by circle P. So let's look at some simple single-phase systems. So let's look at P equals 1. P equals 1. So how about pure water? Pure water, liquid. I have a beaker of water. It's uniform in chemical composition, physically distinct, mechanically separable. How about how about white gold? White gold. White gold consists of an alloy of certainly gold, to which we add silver, and we add nickel. And these are all FCC metals, and at the atomistic level, you have them substituting for one another on the gold lattice. And so I have uniform chemical composition. I have no boundaries. There could be grain boundaries, but that's different. But the grain boundaries do not represent something that is a difference in chemical composition. So this is pure, and this is a solution. So if it's a pure material or a solution, it will qualify as single phase. Okay? Let's look. So here's a liquid, here's a solid. Let's look at a gas. How about air? Air is a solution of nitrogen, oxygen, argon, increasingly CO2. In the city, when you got coal burning for electric power, there's SO2. Oh, let's not forget our pal nitrous oxide. And if you live near an Alcoa smelter, you'll have CF4. If you live near a magnesium smelter, you'll smell chlorine. But in Cambridge, mercifully, we just have to enjoy these. And this is all single phase. You don't see the gases settling according to density. They mix intimately in all proportions. And one more solid, calcium zirconia. We talked about this one before. This is the lime-stabilized zirconia for oxygen sensors, and I'll show you later that this is the material that's used for the faux diamond. This is a solid solution, calcium ions sitting on zirconium sites, so this is single phase. There's no calcium islands, calcium oxide islands, and zirconium oxide islands. This is a solid solution, so therefore it's all one phase. Now let's contrast that to something that's two-phase to get a sense of what the difference is. So instead of pure water, just liquid, suppose I have ice cubes in water. Ice cubes in water. It's still pure. I didn't change the composition, but I've got two different states. I've got a solid state and a liquid state, and this fits the definition. In other words, the ice floating in the water is uniform in chemical composition, and it's physically distinct. Or I can say I can put a boundary around it, and I can isolate all of the ice cubes, and in fact, these are mechanically separable. I could pull out all of the ice cubes and be left with only the liquid. Okay? Solid and liquid. Two different phases because they're two different states of the same material. I think we also looked at milk. We looked at milk, and milk has fat globules in the aqueous phase, in the aqueous solution. All right, so I've got fat globules. They're very tiny, and they scatter light, but if we got down to the micro level, we could find these fat globules as something that's mechanically separable, physically distinct, and of uniform composition and different from this. So this is two different phases because we have two different compositions. We have two different compositions. And lastly, there was the Visions cookware, the pyroceram. The pyroceram, that was the glass ceramic. The glass ceramic that's 95% crystalline and 5% glassy. So what you have here is you have a glassy phase, glassy matrix, and crystalline precipitates. Okay, so again, we don't have a change in composition, but we have a change in order, in atomic order. So the glassy phase and the devitrified phase, so we can actually draw boundaries around all the crystalline precipitate. So I hope this gives you a sense of what's going on here. The second thing is that these phase diagrams are drawn under conditions called equilibrium. That's why we talk about stability. So let's define equilibrium. Equilibrium is a condition which represents the lowest energy state of the system. The lowest energy state. In other words, if you take all of the constituents and give them infinite time and the energy they need to achieve the lowest energy state, this is where they will get to, and we will know that it's the equilibrium state because the properties are invariant. Properties are invariant with time. This is sort of like a steady state, but steady state is something that could be sort of locked in on the road to stability. So this is the ultimate stability as contrasted with metastability. Metastability is something that's steady state but could get stabler yet, and the example of metastability is diamond, which is not the stable form of carbon at room temperature, but diamond was formed under different conditions and then brought under ambient pressure and temperature, but the activation energy to convert is so high that it stays apparently stable, but in point of fact it's metastable. Another one is metallic glass. Metallic glass. We know that metallic glass was formed under high quench rates. If you take metallic glass and heat it moderately, you will give it sufficient activation energy to then jump from this glassy state to the crystalline state and ultimately achieve its equilibrium value. Its equilibrium value. So those are examples of the equilibrium and metastability. And then the last thing, as you noticed, I talked about pure materials and then multi-component materials. They have different elements that are mixed, and so we need a counter, a metric that details what the level of chemical complexity is, and for that we call into play a term called component. Component. And it's the measure of chemical complexity. Measure of chemical complexity. What do I mean by that? In the simplest terms, how many bottles do I have to pull off the shelf to make this thing? Okay? Bottles off the shelf. And again, this is best given by illustration. So I'll show you a mix of components and phases. So we'll do a little matrix here. Start on a new board. So. Okay, so across the top, I'll look at single phase and dual phase, and down the column, I'll look at one component, two component, three component systems. So the simplest is up here, 1-1. One phase, one component, so that's pure water. Pure water, all liquid. Single phase, single component. You can say, but don't you need hydrogen and oxygen? Well, if you take one of the thermal classes later, you'll learn that the hydrogen and oxygen are linked by stoichiometry, so it's still one bottle off the shelf. There's no variation in the hydrogen to oxygen ratio. Diamond, even though it's metastable, it is, all I need is carbon, and it's single phase. There's no change of phase across the diamond. In many cases, the diamonds that you will see, they're all single crystal. Don't ever go to the jeweler and ask for polycrystalline diamond. It's not going to be very pretty. Okay, please remember that. So let's look at something that's now two components. Well, that would be calcia zirconia, right? It's one phase. It's a single solid solution, but I needed two bottles. I needed a bottle of calcium oxide and a bottle of zirconium oxide, but they mix intimately, and I have a single phase. And then the white gold is the gold, the silver, and the nickel. Three different elements. They mix intimately, and they give me a single phase. Over here, I've got one component, so I'm working only with, say, water. So this will be the ice water, or I call it slush. Ice water, slush. Two phases, and they're in equilibrium. So this is at 0 degrees C, and they're stable over time, all right? The lowest energy state, invariant. So the slush remains stable. So you can have dynamics. Some of the solid dissolves into liquid, and some of the liquid freezes out as solid, but the net change is 0. Stable, ice water, slush. Second one, we saw this when we talked about solubility. We looked at the mix of carbon tetrachloride and water, two liquids. We shake them up, and they phase separate. I've been using that term, phase separate, two phases. There's an organic phase, or if you say a carbon-rich phase, a nonpolar phase, and a hydrogen-bonded phase. So these are immiscible. They're immiscible, and I will have two components, two phases. And then the last one, this would be the visions. The visions, because that consisted of lithium oxide, alumina, and silica. I need to get three bottles off the shelf. Remember, I had a network former, a network modifier, and an intermediate, and that gave me this remarkable two-phase mixture that I triggered the X solution of a crystalline phase. So now let's look at some real examples, stability maps. So I want to start, learn to crawl before we learn to run. So let's look at simple ones. So we're going to put C equals 1. So this is pure materials. Pure materials. C equals 1, one component. And we're going to look at, since we have C equals 1, it's fixed. All I have left then, we have pressure, composition, temperature. Composition is fixed because it doesn't vary here, so I just have to look at P versus T. Those are the only variables that I have to deal with. So let's look at some of these. And the first one I want to look at is one that you're pretty familiar with, water. Let's look at the phase diagram of pure water. So we're going to plot how the phases of water vary over pressure and temperature. And I'm going to plot temperature in degrees Celsius, and I'm going to plot pressure in atmospheres, although I'll give you the conversion to SI. So let me just put the general diagram on. It's sort of a Y-shaped looking diagram. So lowest temperature, this is where we have the solid regime, solid water ice. The highest temperature must be where we have the gas or water vapor, and in between we have the liquid. And these lines represent the equilibria. These lines, this one is the equilibrium between liquid and vapor. Liquid and vapor. So this is a liquid equals vapor coexistence curve. Coexistence curve. And it's not a single point. And this one here is solid liquid coexistence curve. Solid equals liquid coexistence curve. Now you know some of the data points on this graph. We live at 1 atmosphere. That's our world, the 1 atmosphere isobar. So let's put P equals 1. And you know that at 1 atmosphere, pure water freezes at 0 degrees Celsius. So that's the point along the solid-liquid coexistence curve at 1 atmosphere applied pressure. And furthermore, you know that at sea level, where we have 1 atmosphere pressure, the liquid turns to vapor at 100 degrees C. At 100 degrees C. So when we go to Mount Everest, we're over here. See, we're at lower pressure, and if we're at lower pressure, we're at lower temperature. And then if we're in the radiator, the cooling system of the car, we applied a higher pressure. We trapped in a higher pressure and thereby extended the temperature range over which the liquid is stable. See, at 2 atmospheres, the liquid is stable over a wider range of temperature. At 1 atmosphere, it's what we know 0 to 100 Celsius, and at lower pressures, it's stable over an even narrower temperature range. So the boiling point, I'm showing you how it varies as a function of pressure. And down here we have, this is solid equals vapor coexistence curve. Below a certain pressure, you can go directly from solid to vapor. If you hang your clothes out on a clothesline and it's minus 20 degrees Celsius, the first thing that happens is the water freezes, but if you come back hours later, the clothes are dry. What happened? Did somebody come in a truck, grab all the clothes and take them down to the laundromat, put them into the dryer, and then come back and hang them on a clothesline? How did it happen? Went directly from solid to vapor. This is sublimation. This is sublimation. Here, liquid goes to vapor is called evaporation. Vapor goes to liquid is condensation. These are the phase transformations. Solid goes to liquid, you know, that's melting. And liquid goes to solid, that is solidification. And I say that without prejudice. It could be to form the glassy solid, or it could be to form the amorphous solid. And sublimation talks about both directions. Vapor to solid or solid to vapor is sublimation. So this is a coexistence curve. So along here, we can even put some labels. We can put over here, single phase, over here, single phase, and over here, single phase. And along these coexistence curves, liquid equals vapor, so I have 2 phases along all the coexistence curves. Along the coexistence curves. Look at this point here. That's a curiosity, isn't it? What do I have here? According to this diagram, I have solid, liquid, and vapor in equilibrium. This is ice cubes in boiling water. Ice cubes in boiling water. All three phases at this point here. And this point, first of all, as you can imagine, not to scale because some of the features are rather subtle and wouldn't be seen if I drew this to scale. This is at a very slight elevation in temperature. It's about 1/100th of a degree above 0 Celsius. And the pressure here is about, it's not about, I know what it is. It's 4.58 millimeters. I'm going to squeeze that in here. It's 4.58 millimeters of mercury. And you need to know that 1 atmosphere, if you remember Torricelli and his vacuum tube, is 76 centimeters or 760 millimeters of mercury. So that's the pressure. It's 4.58 millimeters. And so if you were to take water, pour it into a beaker, cover the beaker with some enclosure that allowed you to pump the temperature down, eventually you would pump the pressure down. Eventually you would reach the pressure at which water boils at room temperature. Water boils at room temperature. Remember this number, 2020. 2020. Roughly 20 degrees C, 20 millimeters of mercury. Round numbers. It's not exactly that, but it's very close. Right? So if you get 20 millimeters of mercury, you'll have boiling water at room temperature. But if you get down to 0 degrees C, just 1/100th of a degree higher, you have all three phases. Ice cubes with water boiling in liquid. So here we are with all of the different phases. And, this last thing I wanted to tell you. Last thing is, you see this slope here? See this slope? It's a negative slope. And it kind of puzzles me, because when you look at it, normally you'd think, you see, if you go at a constant temperature, let's say we start at 0 degrees and very, very low pressure. So we have something that's a gas. And then we press atoms closer and closer together, and then it says you make a solid. And then, at the constant temperature, you press the solid atoms closer together, and it says you make a liquid again. Doesn't that sound kind of backwards? Wouldn't you think that you start with gas atoms far apart, then you move closer, you get liquid atoms, and you press the liquid atoms and you get a solid? But water is special. Water is special because the bonding in the solid is more open than bonding in the liquid. And I can look at this and say, because when I press from solid to liquid, this tells me that the density of the solid is lower than the density of the liquid. I look at that and I say, ice cubes float. Ice cubes float. And there are other systems for which the same happens. Here's silicon. Look at silicon. Here's the phase diagram for silicon, pressure versus temperature. You see down here, it's FCC, the diamond cubic structure. And if we go, there's the melting point of silicon. We go to the liquid. It's got more nearest neighbors. How many nearest neighbors does the solid have? Its sp3 hybrid has 4 nearest neighbors. Most liquids have about 6 nearest neighbors. So when you have these open structures like silicon, germanium, the silicate glasses, and ice, you actually go to a more condensed system when you first liquefy. And this is how you skate, by the way. You know, you're down here at 1 atmosphere, about -5 degrees C, and you put your weight on the blades. So that's a mass, which then becomes a force on a small area, which becomes a pressure, and then that allows you to cross this line. So you glide on a thin film of water. And if the temperature gets really cold, if it's down here at around -20, and I've had the pleasure of skating when it's -20, my mass converted to appropriate pressure on the blades is not high enough to cross this line. And the skating experience is very different, because now it's just steel blades on ice, and you don't get traction. To put it simply, you fall. Okay, you fall. Not good. Not good. Okay, so let's look at a few others. If we contrast here, this is aluminum, a simple FCC metal, and what we see with aluminum. In this case, it's normal. Liquid has about 6 to 8 nearest neighbors, and the solid has 12 nearest neighbors. So the solid is denser than the liquid, and you see that in the phase diagram. Here's nitrogen. Nitrogen is, let's see, what do we have? It's at 1 atmosphere pressure. Its melting point is 63 Kelvin. Its boiling point is 77 Kelvin. You remember that because MIT is 77 mass Av. So nitrogen boils at 77 Kelvin. And the triple point is down here. It's about 1/100th of a degree below. and it turns out it's about an eighth of an atmosphere pressure. This is the triple point of nitrogen ice in boiling liquid nitrogen. But this has a positive slope, so this means that the solid nitrogen ice sinks to the bottom of the liquid nitrogen. And I thought, since it's Friday, maybe we could have just a little bit of fun here with the liquid nitrogen. So I'm going to get dressed first. I have to practice safe science. I have to set an example for you, you see. This year, one of my staff, Patrick Trappa, said, why don't you wear a lab coat? So I said, okay, try to do this properly. Which design house did you go to for this? Valentino, Versace? Okay, so what are we going to do? Oh, we're going to get some nitrogen. Let's get some nitrogen. We'll have some fun with it. So we're going to be working at 77 Kelvin. And for those of you in the back, we're going to put this up on the monitors. Oh, no food in the laboratory, so let's put that over there. Okay, let's pour a little bit of this out. Ah, fantastic. Okay, so see what are we going to do? So first thing we'll do is let's look at glass transition temperature. So I have some rubber gloves. Oh, I have to face Craig over this way. Okay, Craig, I'm going to do it this way. So here's some rubber gloves, and so you can hear that they're acting elastic. They're above their TG. So this is just the covalent bonds. And what I'm going to do is pour a little bit of nitrogen in here. I don't know if you noticed, but these gloves are chiral, just in case you noticed this. I chose chiral gloves. Okay, so now, see? So they're below the glass transition temperature. Oh, I'm sorry, Craig. Here, you get that? So we'll do it one more time. Okay, gone. Glass transition temperature. Also, if you wanted to drill the rubber stopper, of course, now you can hear. Oh, I got to keep doing it this side. So you can hear that it's rubbery. I'm going to drop it in there and let it mind its own business. Oh, saran wrap, it's also got glass transition temperature. So we can show that, getting it into liquid nitrogen. Okay, so you hear how it's flexible. Now, what we'll do is we'll put that in there. Okay, now you can hear how it changes. It's below the glass transition. I should have been wearing gloves and all that, but, forget it. Okay, how about protein? Oh, the other thing we can do, is I want to make some liquid oxygen. So I don't know, can we just cut to the computer slide for a second? I want to show people what we're going to do here with this next one. All right, so what I'm going to do is I'm going to put a graduated cylinder inside, fill this with liquid nitrogen, and these are the boiling points of oxygen, argon, and nitrogen. And nitrogen is at 77, so this is all 77 Kelvin, but oxygen condenses at 90, so we're going to make liquid oxygen with a little bit of argon ice. I'm just going to let it sit there for the balance of the lecture, and maybe at the end we'll see some of the liquid oxygen. So let's just pour that. Okay, so we'll let that work. And, oh yeah, how about proteins? We said they were polymers, so let's see if we can do something with the proteins here. Oh yeah, we're going to put the roses in. They have glass flowers at Harvard, at the museum, Fogg Museum. We have glass flowers here at MIT. See this? So, okay, so this is a rose. It's very soft. It's just nice. Okay, watch this. Okay, let's go. It's not a kitten. I mean, come on. Maybe it only works on roses. Maybe we should do one more. It's got to be a scientist. You don't know. Maybe it's just roses that do this. So let's look at this one. Glass transition temperature. There it is. Okay, so we got that going. We'll let the oxygen condense. And let's see, let's go back to the computer. I think we're going to take a break and go back to some more learning here. Yeah. Okay, so here are some, hang on, there's one other one here, I think. I got it up here. All right, so we've seen this one. Here's nitrogen with all of its different solid phases. Nitrogen actually has different crystal structures, and so this diagram shows what's going on. As you change pressure at constant temperature, here we are still down around minus 70 Kelvin, so there we go from liquid to solid. It's HCP, and then it becomes simple cubic, and then rhombic, and so on. So this property that certain elements have multiple different multiple different crystal structures is called polymorphism. So these are called different polymorphs. You've already heard that iron has, in some instances, BCC crystal structure and FCC crystal structure, and the phase diagrams will reveal when these transitions occur. Here's carbon dioxide, solid liquid gas. It's got a positive slope. What's interesting about carbon dioxide is, look here, the 1 atmosphere isobar takes you directly from solid to gas, so it doesn't go liquid, and that gives it value as a refrigerant, because when it gives up its enthalpy of transformation, you don't end up with a liquid which can mess up your contents, and so this is often used in shipping certain materials. So we've got some here. Let's play with some dry ice. There's a great big ice cube here, but there's some that's already broken off, see? So this, okay, so here we are. This is the big ice cube. I guess Craig is going to want to see this, so let's let Craig and the people watch the video. Well, this is what I call an ice cube. Okay, now this is at minus 78 degrees C, and so it can go directly. You're seeing it's sublime. Let's see, we can do some things. Just to prove, let's prove that it's going directly from solid to gas. So I have just some plain spring water here, non-carbonated. This is flat. Okay, so this is flat. I'll put that on the edge there for Craig. And then just to show that we're going directly, I can take this. Okay, see? I'll hold still, Craig. So there we go. You see the bubbles coming off? Giant bubbles, see? Yeah. So we're making CO2 in water. And this is good. I want you to notice something. You know, you can buy this bottled water, and I don't know if you can see, Craig, I don't know if you can catch this, but you see, they have these tiny wimpy bubbles. We have big bubbles. We have big bubbles. So that's CO2. Let's see, what else have we got going? Let's see if we still have some liquid. We've made any liquid oxygen yet. Oh yeah, there's just a little bit. He won't be able to pick it up on the camera. Okay, so now, the last thing I want to do is to go back to the computer image, if we could, please. Okay, so we've got carbon dioxide. All right, here's a couple other phase diagrams. Zirconia, I mentioned to you that zirconia, this is just pure zirconia, ZrO2. And what do we find? Cubic is the form that gives you that faux diamond, but look, it's stable only above about 2,000 degrees C. So if you're going to give your sweetheart that faux diamond, that's going to be too hot. It's too hot. So what we're going to learn next day is how to open up this range of stability, the way we opened up the range of liquid stability by adding ethylene glycol to water, and see if we can get cubic zirconia stable down to room temperature. Right? But normally it's monoclinic, then it goes tetragonal, it goes cubic, and it goes liquid, and so on. Then it even goes vapor. Here's carbon. At room temperature, over a wide range of pressures, graphite, hexagonal close packed. Then at elevated pressure, it becomes diamond. And here's liquid carbon. It turns out that by judicious choice of chemistry, people at General Electric about 30 years ago reasoned that steel consists of carbon and iron. And if we quench steel, we end up with carbon in the iron lattice. If we put too much carbon, the carbon will exsolve as precipitates. Well, if we could exsolve at elevated pressure, could we get the carbon to exsolve not as graphite, but diamond cubic? And they did it. They generated artificial diamonds. And one of the leaders of the team was a Course 3 alum from MIT, whom I met years later on a committee in Washington in connection with the aluminum industry. And he told me he was in the team that went to London to negotiate with De Beers, the big South African diamond concern. They were scared because General Electric reported that they could make artificial diamonds. And General Electric had reported that they could make large artificial diamonds. Well, large, they were trying to make diamond dust. They actually had one that was about 1 millimeter. It was tiny, but De Beers was nervous. And the fellow's name was Rod Hanneman, and he told me the thing that scared him most was not sitting down with De Beers, because he had them bluffed. The hardest thing was getting through British customs, because he had this on his person. Now, if he opens up and they see all of this diamond material, remember, artificial diamonds don't exist yet. So he's going to tell the customs agent, well, these are artificial diamonds. So I don't think that's going to work. So there's always the, what's it, the early bird gets the worm, but it's the second mouse that gets the cheese. So you can be too early sometimes with that. Okay, here's bismuth. Here's bismuth. Bismuth has a lot of phases. Look at all the different phases of bismuth. And look at here. What does this tell you about the solid bismuth? It will float in liquid bismuth. And then if you go to high enough in pressure, it compresses. Here's sulfur. This sulfur is really one confused element. Look at all the solid phases. Look at all the liquid phases. Sulfur is one mess. Look at. So it has allotropes. Allotropes are different bonding forms. For example, oxygen can exist as atomic oxygen, the molecular oxygen O2, and O3, which is ozone. So we say that O2 and O3 are both allotropes of oxygen. Well, sulfur has 16 allotropes. 16. It exists as discrete atoms, as the dimer, this hexamer. The common solid form is this 8-member circular linkage, and then it polymerizes in the melt. So here's the low temperature. Room temperature sulfur is rhombic, and at elevated temperature it goes monoclinic. It's a solid-solid phase transformation. That's what you're seeing in that phase diagram. When you look back here, that's what all this is. There's the monoclinic and then the rhombic. All right? And then, if you melt it, at first it gives this straw-colored liquid, which they call lambda, at 119 degrees. And around 160, this turns into the rings start to open up, and it turns an orange color at 160. And then this is at some elevated temperature, about 200 degrees C. They poured this long polymer sulfur goo into water, quenching it, and guess what you form? You form a glass. It's plastic sulfur. So all of this is happening as a result of the different phases that are present. So this is forming plastic sulfur. The last thing I want to tell you about is this last phase, supercritical fluid, which is a very high temperature, high pressure phase where you can't tell a gas from a liquid. You can think of it as a highly compressed gas or a highly rarefied liquid. The bonds get far enough apart that the liquid is behaving a little bit differently. The solvation properties are those of a liquid, but here's what happens. In the supercritical fluid, you have transport properties of a gas. So you have something that's liquid-like in terms of its ability to solvate things, but it has gas-like diffusivity, gas-like viscosity. And this is very, very much in the research agenda these days, using supercritical fluids to attack things like toxic waste and so on without having to resort to very aggressive solvents. It's no sense going after aggressive toxins when you have to use aggressive organic solvents, but this will give you something of low polarity, dissolving nonpolar things. And here's one that you use more often than you know, decaffeinating coffee. Uses solvent extraction. When I was your age, they actually used this stuff called methylene chloride. I subsequently used it in stripping paint. It's very vicious. You see, the trick in decaffeinating coffee is to get the caffeine out, but not to brew the coffee. You want to selectively get the caffeine. So now they use supercritical carbon dioxide. So carbon dioxide leaches out the caffeine but doesn't touch the coffee. So you get up into that temperature pressure regime, leach out the caffeine, and then you change temperature and pressure, and now you have this pregnant liquor that is exceeding the solubility product, and now you exsolve the caffeine, and then you reflux the CO2. And that's how we go about with the coffee. The last thing I'm going to do before I introduce, someone's going to tell you about some other activities that will happen during IAP, is to tell you about, I guess this lesson is that there are no depths, there are no limits to the depths of human stupidity. This will tie in denaturing of protein from last day. This is a news thing. Dick Krominga, a principal at Silverton High School, said, this is in Silverton, Oregon, and I'm not making this up, said a pep rally stunt that burned 4 students won't ever be repeated. The 4 suffered severe burns on their buttocks from sitting on blocks of dry ice. The girls were chosen by their classmates for a stunt to see who could sit on the ice the longest. The dry ice, or solid carbon dioxide, can be as cold as 112 Fahrenheit below zero. The 4 were treated at Silverton Hospital. Dr. Frank Lord said some of the girls may need skin grafts. They've denatured the proteins. Right? This is a quote. The truth is, I've never seen any frostbite on this part of the anatomy. Anyways, it goes on about how this was tied in with some football homecoming, and somebody just didn't pay attention.